All right, section 3.5. What we're going to do in this section is much like what we did in section 3.4, but we're going to do it now for multiplication and division as opposed to addition and subtraction. We're going to start in a kind of different way. It's not going to look like there's a direct application, but we'll get there, I promise. So let's take a look first at some properties of exponents. So we've already looked at this particular definition of what an exponent is. If I have a to the n, this is a times a times a times a, all of this n times. For a rational number a, we call a the base, and the n, or the exponent, is the n is called the exponent. And what we're going to do first is I'm going to show you what the rules are, sort of like these are the rules, and then I'm going to explain to you a justification for why the rules actually are correct, okay? I don't think it's always, in fact, most of the time I think it's a bad idea to just give you a formula and say use it. If you can't remember or if you can't learn why it works, then it's probably not something you're going to remember later. And so I like to show you the why behind the rules. The first one, it says that when I have a base that's the same, right, a on both of them, raised to exponents, that I add the exponents together. So this is a to the m plus n. So multiplication of bases, same bases with exponents, adds the exponents. On number 2, which is beneath it, it's the same thing except it's division instead of multiplication. So what do you think is going to happen instead of addition of exponents? It is. It's subtraction of exponents. Again, I'm going to show you the why in a little bit, but it is subtraction. Now 3 is different. 3 is different than number 1 because you don't see the base written again, right? I don't have two a's written down beside each other with exponents. I have an exponent raised to another exponent. And when that happens, we actually multiply the exponents. And then on number 4, when I have a product, AB, raised to a power m, this is the same as having a to the power m times b to the power m. And you might feel like, in some sense, that it sort of distributed the exponent over the multiplication. Now, when we are using these properties in a little while later, we're going to use what I just told you, okay? So what I'm doing on the next slide is not meant for you to have to recreate. I'm not going to ask you on a test, show me why this rule is really how it works. That's not my point, okay? My point is to give you some background so that hopefully somewhere along the way when that smart aleck kid in your class, no, I mean that precious little boy in your class asks you, but why? Even if you don't remember, you can be like, I remember somebody showed me somewhere and I can figure that out for them, and so I can answer the but why. Because saying because I said so or that's the way the book does it is really not sufficient as a teacher for you to be able to answer that way. Okay? So I'm going to show you the but why. Why does that work? And I'm going to do that with some examples. So the first one we said is that we add the exponents together. That's what this justification is going to be for. And I'm going to do an example for you where we put some numbers in. So this is not a proof in the sense that it works for every number. I'm just giving you an example of it so you can see it working. We're going to do a cubed, a squared. Okay? And what we're going to do is we're going to actually write out what does it mean. What does a cubed mean? Good. It's a times a times a. And what does a squared mean? It's a times a. And if you count them real quick, because you guys are really good at counting, just like me, how many a's did you just write down? 5. So that's a to the 5th. And you can see very quickly that the reason that 3 and 2 become 5 is because they're added together. Right? So a lot of kids, and maybe even you, are tempted in this particular case to multiply the m and the n together. But if you do a real simple, quick example, you can remind yourself that no, it's not multiplication, it's addition. Okay? All right, the next one we said was supposed to be subtraction. Whoops. Like so. So then, Let's do an example. We're going to do a to the fourth over a, which is the same as a to the first. Just a reminder, okay? So just like last time, a to the fourth means I have 4 a's, right? A to the first means I have 1a. So what can I do when I have a divided by a? Yeah, you can divide one out. You can reduce it by a factor of a. That leaves me with 3 a's on top. It leaves me with the number 1 on bottom. You can write it in if you'd like. But a times a times a is a to the third. And again, how do you get from 4 and 1 to 3? You subtract. Okay? Again, you might be tempted when you're looking at it to think, I divide a and m, but a real quick example shows that we actually don't. We actually subtract them. All right, this one said that it's supposed to be multiplication, like so. So again, we'll do an example. We're going to do a squared cubed. Okay, well, inside the parentheses, a squared, that's just a times a, right? That's what a squared means. And then what does it mean to take a quantity and cube it? You write it 3 times, right? So this is the same now as AA, AA, AA. And again, count them up real quick. How many A's did I get? 6. And again, how do I get from 2 and 3 to 6? I multiply. Now the last one, AB to the M, says that I should be able to distribute the M to each factor. All right, so let's do AB cubed. So just like on the last one, cubed means multiplied by itself 3 times. So this is AB, AB, and AB. And I'm going to reorder them. I'm going to put all the A's at the beginning and then all the B's at the end. Why am I allowed to do that? Don't take that for granted. Why? Right, but what property allows me to do that? Commutative is one of them. Associative is the other. Commutative means I switch the order of things, right? And then associative means that I regroup. In other words, I'm grouping the A's together and I'm grouping the B's together instead of A's and B's in the same grouping. And then I can write them as A cubed and B cubed. So again, that property only works, that example of an exponent rule only works because of the properties of commutativity and associativity of real numbers. In particular, whole numbers, because we're still working with whole numbers. Okay, so that aside, I'm not asking you to do what I just did on those 4 problems on the next problems, okay? I'm asking you to simply use these properties at face value. That's why we have them, is so that we can utilize them. So we're taking a look now at a couple examples. I think I have 3. 2, I was wrong, 2 examples. And we're going to simplify each one of these. So taking a look at the first one, they all have a 5 as their base, right? So that's good. What can I then do with the exponents? Add them. So you don't necessarily have to write this step out. If you're okay without writing it, that's okay with me. But this is 10 plus 2 plus 4, which gives me a grand total of 16. So this is 5 to the 16th. So if you jump just to the 5 to the 16th, that's fine. Okay, part B has more than one way to do the problem. How do you think, or what do you notice is different about B than A? The bases are not all the same number, right? So there's two ways to do the problem. One way is to try to get both ways try to get the bases to match. One way is to break the 6 down into pieces that match the other pieces. Because what is 6? 2 and 3, right? It's 2 times 3, and that's what the other two pieces are. The other way is to combine the 2 and the 3 together so that they become a 6. All right? I'm going to show you how to do both ways because it doesn't matter to me which way you do it. They're just two different perspectives of the same problem. So let's start with the breaking it down first. If I were to take the 6 and I were breaking it down, it would be 2 times 3. And it still has a power of 4 as the exponent, right? So properties of exponents say, what can I do with that 4? Distribute it, right. So this is 2 to the 4th times 3 to the 4th. And then I still have a 2 cubed times 3 cubed. Yeah, now I can group the 2's, and I'll just highlight mine. How many 2's are there? 7, so this is 2 to the 7th. And then I can do the same thing with the 3's. And how many 3's are there? 7. So one answer to this problem is 2 to the 7th times 3 to the 7th. Now in some fashion, this is a little bit more simplified, you can think of it that way, than the other version I'm going to show you, because 2 and 3 are primes. So some people would say that this is the most simplified way to do this because they're prime numbers. The other way I'm going to show you how to do this, some people would say, is more simplified because it's more compact. It doesn't have all these pieces in the end. And so for that reason, it should be considered the simplified version. All right, so the 6 is going to stay on this one, 6 to the 4th. And what we're going to do is we're going to take these two and we're going to sort of visually recognize that they both have a power of 3. Do you see that? So I'm going to, if you will, undistribute the power of 3 and put it on the outside. It's just that same property number 4, but backwards. I've pulled the 3 out. Well, that's good, because what's 2 times 3 then? 6. So now I have 6 to the 4th, and I have 6 cubed, and they have the same base, 6. So this would be understood then to be 6 to the 7th. And I do hope that as you look at those two answers, you see why they're the same, that you can make amends to the fact that those are just the same value expressed differently. And I also hope you can realize why you could look at either one of them and say, that's the simplified version. Simplified from a different perspective, okay? So as far as I'm concerned, either of those answers are perfectly fine. Neither one's really better than the other one. It just depends on what you would want to do with it next. Okay, so the first part of this lesson is all about taking a look at multiplication facts with exponents. Now we're going to look at multiplication facts when we're multiplying values that don't have exponents together. And these are the different algorithms that we're going to start with, so this is going to feel like what we did in section 3.4. All right, so our first algorithm is called the expanded standard algorithm. So just as a aside, let's do the standard algorithm first so that I can show you why we call the next one the expanded version. So your standard algorithm with multiplication, we do 48 times 32, and we're going to write it, sort of longhand like this from early on when you first learn multiplication. And the first thing you do is you start with which number when you're multiplying? The 2 and the 8, right. So we start with the 2 and we say, what is 2 times 8? 16. And then we do this thing where we write a 6 down and we carry a 1. And then we say 2 times 4 because now we're not even worrying about staying on the same column. We are now going on a diagonal. So that's fun. 2 times 4 is 8, and then somehow in the middle of the multiplication we're going to add the number 1 in, and we get a 9. And then a mysterious 0 shows up out of the middle of nowhere. Oh yeah, this is what kids are thinking when you're teaching it to them, like, wow, look, there's a 0 now. And then we go over to the 3, and again we do this weird thing where we say, okay, I'm going to take the 3, and I'm going to go on a diagonal again. 3 times 8 is 24, so I write down my 4, and then all of a sudden the 1 that's on top of the 4 becomes a 2. That's what it does, right? And we say 3 times 4, and that's 12, and then again in the middle of my multiplication I add 2 to it so that I get a 14, and if that weren't all well good enough, at the very end we add again. And we say 6, and then even the addition here ends up giving me some carrying or regrouping involved. 9 and 4 is 13. And then I've got my 5 and I've got my 1. It's so awkward. It's super efficient and you're all super comfortable with it because you've been doing it forever. But this is not necessarily intuitive. Now there's reasons that we do all of the things that we just did. There's a reason that the mysterious 0 showed up. There's a reason that I wrote down a 1 in the middle of the multiplication I added. There's reasons behind all of that. But those are usually glossed over in the effort of making sure that kids can get to the point of actually just doing it efficiently. Okay? So I'm going to show you the expanded algorithm. There's 2 versions for the expanded algorithm. The first one's actually called expanded algorithm. The other one is the second one here. It's called partial products. So let me show you what the expanded algorithm looks like because it at least takes some of the mystery away from what's going on. So we're going to take the number 48 and we're going to separate it into its pieces. That is by place value, 40 plus 8. And we're going to do 30 plus 2. Okay? And what we're literally going to do is we're going to multiply up and over, okay, just like we did with the other, with the standard algorithm. But we're actually doing it with the numbers with their place value. So like when I multiply 2 times 4 in a minute here, I'm not multiplying 2 times 4. I'm really multiplying 2 times 40. That's really what I'm doing. Okay, so if I do this piece, the pink's showing up, okay. I can do 8 times 2. And I can do 40 times 2. And then I'll do this one. Hang on, let me use another color. How about blue? All right, so I have the 30 times the 8, and then 30 times 40. Now, what I just wrote down are the same multiplication facts I did in the other problem, but they're written with the place value taken into consideration. So 2 and 8 is 16, but I just write the 16 down. 40 times 2 is 80. 30 times 8 is 240. And then 30 times 40 is 1200. Now, whether you write them vertically at that point or whether you add them left to right or whatever you want to at that point, I'm tempted to write them vertically with the biggest one on top, so I will. If I go on the right-hand side, I've got a 6. 4 plus 8 plus 1 is what? 13, and I carry my 1 or regroup my 1. 2, 2, and 1 is 5, so there's my 1536. It's more obvious what's going on. It is more writing. There's pros and cons with every one we're going to do. There's more writing that I just did, but it's much more obvious where the numbers all came from and why they combined in the way that they combined. My favorite's the next one. It's called partial products, and it breaks it apart much like that one did. I've got my 40 and 8. I've got my 30 and 2, okay? But the reason I like this one so much is because it models what happens with area. Now I'm going to do the simplified version of it, and then I'll show you what I mean by it models what happens with area. So draw a box. The box is a 2 by 2 box. Okay? The numbers 40 and 8 go along the top. So 48, like that. And the numbers 30 and 2 go along the right-hand side. And while it technically doesn't matter if I do it along the top and the right or the bottom and the left, you'll stick with me, it'll matter in a minute on the next one. So I just always put it on the top and on the right so that I don't have to remember which one matters and which one doesn't, okay? And what we're going to do is we're going to multiply this inside the box. It's just a grid. So in the first top left box over here, I'm going to multiply 40 and 30 because I'm on the column for the 40, I'm on the row for the 30, and I'm going to write the product inside there. That's 1,200. If I go to the right, and again, the order in this doesn't matter, which is also kind of nice. So if a kid gets stuck on one spot and they want to move to a different box and fill it in first, then fantastic, go for it. I have 8 times 30, so that's my 240. This box would be the 40 because I'm on the column for the 40, the row for the 2 to give me 80. And then my last box is 8 and 2 to give me 16. It's the same 4 numbers I just had on the other viewpoint, but it's done in a more visually structured way, I think. So that's kind of maybe why it appeals to me, is because of the structure that's involved. Again, you can add them from where they are, or you can rewrite them out to the side. That's how I think about them, is rewritten to the side. Added together, of course, I still get 1536, just like I did a moment ago. Now let me draw a picture of what's really going on when we're doing this. What I'm really doing is I have the number 48, and if you think about it from an area model, what this means is that I am 40 by 8 wide. Okay? That's what 48 means. I've partitioned it off, 40 and then 8. And then I'm 32 long, so it looks something like this. This is 30 long, and this is 2 long. So graphically, you can see why this is so much more, right? This is 1,200 in space. This is 240 in space. This is 80 in space, and this is 16. And that's where all the numbers are actually coming from in terms of a grid. I know you guys have heard me talk about my daughter Abby before. I'm sorry, Cassidy, yes, first.
If there's 3 numbers that you're multiplying?
It's a good question. You guys are asking such good general, like, extension questions. If you had, say, like 432 times 12, your grid would actually be 3 wide, and it would be 2 long. So you would have 400, 30, 2, 10, 2. And if you did a 3 by 3, same thing. You just have a 3 by 3 grid. Yep. Yeah, so you can extend, this one's, that's nice because it really extends itself very well in terms of the space of the visual drawing. Mm-hmm. Okay, you ready for another one? All right, so I very distinctly remember when my daughter was in 3rd grade and she started doing 2-digit multiplication. And the Abby's, you guys know, she's very bright. She picks up on things very easily. Learning is just not really that big of a struggle for her. And so I have different issues with her. Learning's a struggle more for my son. But she did not understand the standard algorithm here. It just totally, she's fine with it now. She can certainly do it now. But when they started with that, that was just not working for her. It wasn't. And she didn't like partial products, which just hurt my heart because that's the one I like. And so this is actually the one that she liked. She liked the lattice algorithm. So there may be kids in your class who also tend toward one versus another one, and having multiple approaches is never a bad thing. As long as you know how to do them all. That would be a bad thing if you don't know what you're doing. But, okay, that's why I'm teaching you. So let me show you what the lattice algorithm looks like. Okay, so what we're going to do is same numbers as before, 48, 32, and we're going to draw a square grid, okay, and we're going to divide it into half and half again. Okay, so it starts out looking like partial products. That's terrible. Let's try that again. Now, instead of writing down 40, like 40, we write down 4 and 8, 3 and 2. Okay, so we use the single digits. We don't use their place value that they're in. We just use the single digits. Now, we did lattice before. We did it with addition. And do you remember when we did the lattice, we divided each of our boxes into diagonals? We're going to do that again here. So divide up your boxes into diagonals. Now, when we did it for addition, we added row, column, and we put the two-digit number, the top digit on the left, bottom digit on the right. We're going to do the same thing here, except we're multiplying, because this is products, not sums. So in the top left box, I have 4 times 3. So over here is 4 times 3, which is 12. So the top number goes 1, and the bottom number is the 2. Again, this is kind of nice because you can move around at whatever, sort of order you want in your boxes. It doesn't hurt anything. 8 times 3 is 24. 4 times 2, that's the bottom left corner, would be 8. So single digit 8 puts the single digit in the bottom right corner. And then 8 times 2 on the bottom right is 16, so I have a 1 and a 6. Now, one of the things that this does really nicely is it isolates all those single multiplication facts that kids spend like almost all of 3rd grade memorizing, right? Everything that I just did in this table is, the flashcard multiplication facts that the kids learn in 3rd grade. So that's really nice. It isolates the multiplication. And the next step is all about addition. So again, we've got addition and we've got multiplication just like on any of these methods, but both of these last 2 methods, partial products and lattice, separate the multiplication and the addition into 2 separate steps. So you're not adding in the middle of multiplying, which can confuse kids. All right? So let's take a look at what happens. We extend those lines, and we're going to add in the bottom right-hand corner. So the 6 is by itself. Okay, we're only adding values inside my grid, so in some way, you're going to ignore these guys. These were our multiplication facts, the factors. They are not adding anything to it, okay? It's just the addition of the numbers inside the box. Along my next diagonal, this one right here, I have 8 plus 1 plus 4, which is, what is it? 15? 13. Okay, sorry, I was hearing you wrong. So there's a 3, and then I carry my 1. And then again, I add the next diagonal. I have 2 plus 2 plus 1, which is 5. And if I needed to, I would carry something from there. I don't on this one. And then this last number, the 1 over here, adds to nothing else. There's just a 1 left. So my answer is at the bottom, 1536. All right? And we'll stop there.